Okay, so today I'm going to be talking about a particular category of vulnerabilities that I think most developers usually don't think about and generally are not aware of. So if you're going to be writing cryptography code, you need to know about this, and you need to be able to think about it. Okay? So if you're going to be implementing an encryption algorithm, like let's say RSA, or you're going to be implementing elliptic curve operations, then you need to think about this and be aware of it when you're coding. So hopefully in this talk, I want to, first of all, convince you that timing attacks are actually a real problem. And then second of all, I want to introduce you to a style of coding that allows you to prevent timing leaks. So to start off, let's look at some example code here and get a little bit of feedback, ideally. So this example code here is just, it checks an API key, right? So you have an input API key from a client or from a user, and it checks it against the expected key. So it checks to see are they equal, and if they're not equal, then we throw an error, obviously. And it's written in JavaScript. There's no JavaScript quirks here. It's just very simple. I didn't try to trick you here. Nothing tricky about this code. The interesting thing, though, is that there's actually a vulnerability here that could allow an attacker to figure out what is the expected key without any prior knowledge of the key. The problem is actually in how we do string equalities, how we compare strings. So to understand that, we're going to have to do a little detour here and look at how does string equality actually work. So we're going to write some pseudocode here, and again, I'm going to do it in JavaScript, but it could be any language. This is pretty close to what languages actually do when you compare strings. So let's start with a function that compares two strings, string 1 and string 2. So the first step we're going to do is compare the lengths of the strings. So if the lengths are not the same, then obviously the strings are different, so we can return false right away. If the lengths are the same, then we'll proceed onwards and we'll look at each individual character in the string. So first character, second character, third character, all the way to the end. If we find a difference, then we can return false. Otherwise, we'll return true, because we know that they must be equal. Okay, so that's fairly straightforward, and I hope you can follow that. Now, I want you to consider how long does this function take to execute? Does it take the same amount of time every time, or does it take a different amount of time? Well, fairly clearly, it's a different amount of time depending on what the inputs are, right? Because if the strings are a different length, then we know right away, oh, we can return false. If they're the same length, and maybe they're the same for the first 500 characters, you have to get to the 501st character and say, oh, actually there's a difference here, so now we can return false. So these differences in timing are actually very small, but you can measure them if you have the right techniques. You can measure them with a very precise timer. So that's what we're going to be talking about today. Okay, so that finishes our detour. Now, back to our example code. Let's look at how we can exploit this. So first of all, let's assume our API keys look something like this. So this is a fairly standard looking API key used in a lot of applications, and we're using base 16 here. So there's 16 different possibilities for each character, 0 through F. So here's what the attacker does. This is going to be the correct key that we're going to try to crack. The attacker is going to try 16 different keys. And I used X's up here, but that could just be any character. It doesn't really matter. The main part is that the first character in each attempt is 0, 1, 2, 3, all the way to F, right? 16 different possibilities. And what's interesting is that one of these attempts will take slightly longer, just slightly. Number 6 in this case. And the reason for that is that when you get the first character correct, then you have to do one more iteration in that for loop. You have to go, oh, the first characters match, but the second characters don't match. Now we can return false. It takes slightly longer. So now the attacker knows the first character is 6 and can proceed onwards and say, okay, let's try 0 through F on the second character. And they'll find, once again, that one particular attempt will take slightly longer. And the attacker can just proceed and do this for every single character in the key until finally they have the entire key extracted. So lesson number 1 here is that timing differences can reveal information that you did not think you were revealing at all, right? Here, it didn't seem like we were revealing the key to the attacker, but just through this subtle difference, we can actually measure that. So, the question, of course, is these differences are very small, so are they measurable? And, well, the answer here really is that it depends. It depends on what language you're using, what runtime, it depends on what resources your attacker has, and it also depends on whether you're in a particular type of hosting environment. So, for example, on Amazon EC2, you can actually rent a server in your target's data center, which is very helpful, because then you have a low latency LAN connection to your target server, which is great for if you want to take timing measurements. So how do we fix this? The rest of my talk is going to be talking about how we can actually approach a fix to this, and I'm going to assume that you actually care about these problems. Sometimes you just don't care because the context doesn't make sense. So the first thing everyone thinks of is, what if we just added some random sleep commands? So what if we just add some random delays into our code, so that way now the execution time should be hidden, it should be masked. So the first problem with this solution is that you're vulnerable to statistics. So the attacker can take many measurements and then try to average it out and say, okay, this one on average takes slightly longer, so therefore I know this one is actually the right character. The second problem, though, is that people generally want their code to be fast, and sleeping is kind of the opposite of fast. So it's not really a great solution for that, from a performance perspective. But there's actually a much larger issue here that I want to talk about, and that's an issue with adding sleep commands. And the issue here is that modern computers don't just do one thing at once. They actually multitask, and they'll have thousands of processes all running in parallel, not actually in parallel. You have an operating system scheduler that decides, okay, this process will get this CPU core, and this process will get that CPU core, and you'll get it for that amount of time. And of course, the way that it decides, okay, which core to give to which process is not just random, right? There's actually some logic behind it. And one of the things it looks at is, well, is the process sleeping? If a process is sleeping, obviously it doesn't need to be on the CPU right now. So therefore, if your process is sleeping longer, then other processes will get more CPU time. So by measuring how busy the CPU is, you can actually figure out how long your process slept for, and therefore figure out what the actual execution time was, and there we're back to the original problem. So this is a long way of saying that what your program does will actually affect the performance of other programs on the same hardware. The actions your code takes will have these subtle but measurable interference patterns on other code. And this is not only within the context of an operating system, this actually happens across virtual machines as well. So if you're in a shared hosting environment, again, like Amazon EC2, then you can actually record these interference patterns coming from other virtual machines and learn information about what other people are doing. Now, I've talked about one cause of these interference patterns, which is whether your process is sleeping or not, but there's actually many different causes. I don't have time to go through all of them today because it's actually like an entire subcategory of academia. There's hundreds of papers in this genre, so I don't really have time to talk about all of them. But I want to highlight a few of them that are interesting. So one example is memory bandwidth. So if your program is reading a lot of data from memory continuously, and another process tries to read data from memory, there'll be some contention there. There's a shared resource, right? So the other process will tell, oh, there must be someone reading lots of data from memory. Another example I need to highlight is CPU caches. If you can observe the behavior of CPU caches, then you can actually learn what addresses in memory other processes are accessing, which is kind of scary. So that means if let's say your process accesses element number 7 in an array, then another process on that same machine might be able to determine that you access element number 7. They won't be able to see necessarily what's in the array, but they can see, oh, you access element number 7. And that can reveal a surprising amount of information. So this seems bad. You might be wondering, well, will this get fixed in the hardware? Because it seems like a hardware problem. And unfortunately, the answer is it probably won't. And the reason for this is that everything on the previous slide that I just listed is about either improving performance or reducing cost. And unless people stop caring about performance and cost, then these effects will probably persist. So lesson number 2 is that not only do we need to manage the execution time of our code and think about what information it might reveal, we also need to manage what hardware resources we're using, how we're using those resources. So now I'm going to present a solution to these issues, a real solution. So, and of course, this solution is accordingly going to be about managing the execution time of your code and managing the resource usage. So step 1 to the solution is to identify what variables do you actually want to keep secret? What values do you care about protecting? Because honestly, most variables are not that sensitive in your program, so they don't actually need special treatment. So let's say you're writing cryptography software. In that case, you probably want to care about encryption keys. Encryption keys you generally want to keep secret. Also, if you're encrypting messages, the messages themselves are probably secret as well, so you might want to protect those as well. So our goal here is that once we identify which values are secret, then we're going to try to break the relationship between the secret values and the interference patterns. We're still going to have these interference patterns, but hopefully we can make it so that they're not correlated with the secret values. So that way the interference patterns don't reveal anything sensitive. So step 2 is our first rule for writing this secure code. And this rule states that we must not have any control flow that is influenced by a secret value. So what that means is that if we have an if statement, the condition in the if statement must not be itself a secret. Because the reality is that an attacker who's observing the interference patterns can likely tell which direction our code chose to go in, which direction of control flow. So this applies to if statements, also applies to while loops, and the conditions on for loops as well. The second rule and the third step here is to remove any secrecy in our memory location. So I already talked about this a little bit. If you're accessing element number 7 of an array, you have to assume that the attacker can observe that it was element number 7. And the last rule and the last step is simply to avoid these variable time operations. So some CPU instructions actually take a variable amount of time to execute depending on what the values are. So obviously that's not good because that will impact your execution time. A common example is division. So division is a fairly expensive instruction on modern CPUs. So larger numbers typically take longer to divide, and smaller numbers take a short amount of time to divide. Okay, so that's pretty much it. So I want to show a little example here. I have some example code, and it's pretty silly. It's just a function that takes a number x, and either it adds 5 to it, or it doubles it. And it makes that decision based on the value of a Boolean called add. Now, there's an if statement in here. So that means there's going to be an interference pattern indicating whether we added or we doubled. So let's say we wanted to hide that. Maybe we wanted to conceal whether we actually added or doubled. So we can do that, and it will look something like this. Now, I don't have time to explain all this, but basically what's going on here is we're using these bitwise operations like and or, and we're using that to effectively have the same output, where it's exactly the same as the previous code in terms of inputs and outputs, except it's implemented differently. There's no if statement in here, but it behaves exactly the same. There's a catch. Unfortunately, modern compilers are really smart, crazily smart. So a modern compiler might actually look at this code and optimize it back into the original code. It's so smart, it will look through what you're doing here and figure out that, oh, this is actually an if statement, so I'm going to insert an if statement. So first of all, I mean, that's incredible and amazing. Second of all, that's technically correct. I can't really say that's wrong. They're allowed to do optimizations like that. And third of all, that's really annoying because basically our compiler just added a vulnerability back into our code. So how do we fix that? Well, that's painful. So we could potentially just forget about high-level languages altogether, use assembly, go back to the dark ages. We could use high-level languages, but then we could compile them into assembly and then read through the assembly output and look for vulnerabilities. And that also is painful, so hopefully we don't have to do that. And also that's really hard to do, actually, with languages like JavaScript or Java, because JavaScript runs on various different runtimes. Java compiles into JVM bytecode. You can't actually really look at the final assembly output easily enough. So there's not really a clear solution here. And actually, this is largely an unsolved problem, to be honest. I don't know of any great tooling around this that can actually help you solve this in a reliable manner. So now, shameless plug. I'm working on a tool called Rust Timing Shield. So it is a framework for preventing information leaks in Rust code. So basically, you mark which variables you want to keep secret, and then you'll automatically get these errors at compile time if you have vulnerabilities in your code, which is pretty nice. All right, so to summarize, was it? I'll tweet a link to it later so you can see more. So to summarize, I want to get across mainly 4 key points here. And the first 2 are about, you need to think about the execution time of your code and also your hardware resource usage. So, because those 2 things can reveal a lot of information that you did not think you're going to reveal. You can prevent these sorts of information leaks using these 4 steps. They're fairly straightforward. First of all, identify the secret values, and then apply these 3 rules. And last of all, I want to mention that I think there's a lot more research that needs to go into this problem, ideally with teaching compilers to understand these issues, so that way they won't add vulnerabilities back into our code, because that's a pain. So that's about all I've got. If you want to read more about the subject, I do blog periodically on chosenplaintext.ca. I'm also McLean0 on Twitter. I will tweet a link to the slides and to Rust Timing Shield later if you want to read more about that. So thanks for listening.